Hello, my name is Benjamin Rott. I'm a professor for mathematics education at the University of Cologne in Germany. First of all, I'd like to thank Professor Fauzan for inviting me to hold this presentation. Today, I'm going to talk about models of the problem-solving process. Okay, why problem solving? In 1980, the famous mathematician Paul Helmers wrote about the heart of mathematics. What does mathematics really consist of? Axioms, theorems, proofs, and so on. Mathematics could surely not exist without these ingredients. Nevertheless, none of them is at the heart of the subject. The mathematician's main reason for existence is to solve problems. What mathematics really consists of is problems and solutions. So if we want to teach mathematics and not only calculus or calculating, then we should teach about problem solving. Also, problem solving is at the heart of several theories from learning psychology, here for example from Garnier, and it is part of many curricula, for example in the NCTM standards in America or the Bildungsstandards in Germany. So, what is problem solving? Alan Schoenfeld defined this as follows. A mathematical problem is a task in which the student is interested and engaged, and for which a student does not have a readily accessible mathematical means or algorithm by which to achieve that resolution. This implies that tasks are not problems in and of themselves, but depend on the solver, and that most textbook problems are not problems, but exercises. And I want to talk about modeling problem-solving processes. James Wilson wrote, to discuss and investigate the processes involved in problem-solving, researchers find it useful to develop frameworks. Similarly, frameworks are useful for discussing general processes and approaches to problem-solving with students. So you have frameworks. They are used to investigate processes in a descriptive way, and they are used to discuss and help students to become better problem solvers in a normative way. There are a lot of normative models of problem solving processes and almost no descriptive models. So in this research, I'm going to investigate a descriptive model or framework of problem solving processes. From a different angle, there are frameworks of the inner structure and of the outer structure of such processes. Inner structure refers to heuristics, belief, cognitive processes, anything that lies within the head of the problem solvers. And the outer structure refers to this temporal sequence of processes, the organization of the processes, anything you can observe from the outside. And I'm going to focus on this. So my talk is structured in these 5 sections. I start with comparing some phase models of problem solving. There are classic models from Henri Poincaré, Graham Wallis, and John Dewey. You can also count Polya's famous model to these classics, and there are several modern models or frameworks of the problem solving processes that I want to tap into here. Wallis, building on the work of Poincaré, described the problem-solving process in this way. You start working on a problem, really try to solve it, and when you cannot do this, you lay it aside. You do something else, and unconsciously, your mind still works on this problem until finally you come to an illumination, you have the sudden idea of a solution, and then you just have to verify it. Dewey, on the other hand, did not talk about subconscious processes, but only about conscious processes, like finding a guiding idea, reasoning, and testing a hypothesis by action. Polya's famous model of understanding, devising a plan, carrying out the plan, and looking back is very similar to Dewey's ideas and does not incorporate subconscious processes. Polya's model is very famous. It is seminal for mathematics education research, and you can even find it in textbooks, for example, in this German mathematics textbook. Several researchers from mathematics education built on Puglia's work. For example, Mason, Burton, and Stacy introduced this model of the problem-solving process. The first and last phases are identical to Puglia's ones, and they combine devising and carrying out the plan to the attack phase. Schoenfeld also uses the phases suggested by Puglia, but he differentiates devising a plan into the structured planning and the unstructured exploration, where you try out ideas without knowing how to proceed or what your plan might look like. Another example stems from Wilson and colleagues. This is a cyclic model, and if we rearrange the phases a bit, you can also see the similarities to Puglia's model. All the phases are identical. He just highlights the ways to go back and forth between the phases, and that managerial processes are at the center of this. So doing a systematic comparison of these and other phase models, we can look at least these three aspects. Type and number of phases. Almost all the models contain phases like understanding the problem or analyzing it. Some combine analysis and planning. And in Wallace's model, there you have this holistic phase of preparation, where the problem solvers try to do everything until they fail to proceed. There are phases like devising a plan, or Schoenfeld's differentiation into structured planning and unstructured exploration. There is Puglia's carrying out the plan, and Mason's combination of planning and carrying out the plan, the attack phase. Almost all the models contain a verification or looking back phase. Ymer and Ellerton, for example, differentiate this further into evaluation, which is looking back and checking your results, and internalization, which is trying to learn from your experiences for future processes. And finally, there are these subconscious phases of incubation and illumination as described by Poincaré, Wallace, and other researchers. Referring to linearity and non-linearity of processes, we have models like the one by Puglia, where everything goes in a linear way. First you have to do this, then you have to do this, then that. This is a classic example for a normative model, where you are told what to do, and this in a linear way. Then we have models like the one by Mason et al. Or Schoenfeld, who show the idea of going back and forth at the beginning until you come up with a plan. And then you proceed in a linear way until you have your checked solution. And finally, there are models like the one by Wilson et al., which are cyclic all the way, all the phases you can go back and forth. Finally, there is the aspect of metacognition and self-regulation. All the modern authors highlight that transitions between phases have to do something with self-regulation or metacognition. Mason speaks of an internal monitor that you should develop to guide you through processes. Wilson highlights these managerial processes also between phases, and other authors highlight cognitive or metacognitive phases as well. Puglia did not use the term metacognition, but only because this term was not coined when he wrote his famous book, How to Solve It. In Puglia's work, it becomes quite clear that he was well aware of the importance of what we later called metacognition, and Flavel, who coined the term, also referred to Puglia's work. So the research questions for my study are the following. To what extent are existing models of the problem-solving process or elements from these models suitable for describing problem-solving processes of students? Because I want to build a descriptive framework or model. And the second question is, how do differently successful problem-solving processes of students with or without technology proceed? The database are students that were attending a lecture on elementary geometry. In addition to the lecture, the students participated in weekly tutorials, and in 4 of those tutorials we videotaped them. Half of the tutorials used technology, dynamic geometry software, and the other half did not use any technology. They just used paper and pencil to solve problems. Over the course of the semester, we videotaped the students working on 5 challenging geometric problems. And the data are the videos, the processes, and the notes the students wrote down the products. To analyze the processes, I used the protocol analysis framework by Schoenfeld. This framework is based on Puljar's work, and Schoenfeld parses processes into episodes. An episode is a period of time during which problem solvers are engaged in a particular activity or a pattern of consistent behavior. Once a protocol is parsed into episodes, the episodes are characterized. And he defines these 6 types of episodes, which are very similar to his framework of the problem-solving process. You can see an example here. The students read the task, and then they explored it. They tried to solve it without developing a plan or verifying it. And the second example would be this. The students also started reading, then exploring, but these students developed a plan, they implemented it, they came up with a second plan, a second implementation, and then they verified their solution. So without knowing anything about the students or the problems, you can easily see that there are differences in these processes, and we can easily guess that the second group was more successful. To describe the processes of our students, I added additional types of episodes for writing or digression when the students talked about something completely different than the problem. To operationalize Schoenfeld's framework, I used Puljar's writings to better understand the ideas of the episodes that Schoenfeld coined. Coding the processes was done by several independent raters. You can see here how we determined inter-rater agreement, and overall we came to a very good inter-rater agreement score. I want to give you some examples to better understand how this coding works. In the paper and pencil environment, students worked, amongst others, on this problem, the 3 beaches problem. A woman lives on an island that has the shape of an equilateral triangle. On all 3 beaches, there are wonderful opportunities to surf. Part A, where should she build her house so that the distances from the house to each of the beaches is identical? And part B, where should she build her house so that the sum of the distances to all 3 beaches is minimal? What did the students do? For part A, they read the problem for about a minute. They started analyzing the task. Then they developed a plan and simultaneously implemented it. And then they checked if the solution is correct. Of course, they constructed the center of the in-circle. This was not a problem for the students, but a routine task. For part B, they again read the next part of the problem. They started analyzing it, started exploring it, used a second analysis, and then continued to explore until their time was up. You can see what they did here. They measured several points to get the sum of the distances to the sides. Their solution was, because of some inaccuracies in their drawings, that all the points on these angle bisectors have the same sum of distances, And the points that are not on these angle bisectors have a slightly larger sum of distances. This is incorrect. In fact, all the points have the same sum of distances, but they did not get this correct. To give you a second example from the DGS environment, you can see the students here working on a laptop with a dynamical geometry software. The shortest detour problem, given is a straight line G and 2 points A and B outside the straight line. Let C be any point on G. That is, C is freely selectable on G and can be moved on G. We are looking for the shortest detour from A via C to B, at which point C minimum of the straight line G is a path minimal. Describe how to construct the point C exactly. Then, why is the way via C minimum minimal? The students started reading and immediately came up with a plan. They placed A and B on different sides of G and said, oh, this is easy. We just have to move C so that there is a straight line from A to B, because a straight line is the shortest way. And they also used the DGS to measure and verify their idea. Then they realized that there is a second case with A and B on the same side of G. They started exploring this, measuring the lengths, measuring the angles. Maybe it has to do with the angles. Maybe it has to do with something else. When one of the students said, oh, this is so unfair. The first case was so easy and the second case is so hard. And this gave them the idea to refer to the first case. They reflected B on G, and then they again drew a straight line from A to the reflection of B. And then they argued that from C to the reflection of B is the same distance as from C to B, and therefore this is the correct point. And then they wrote down their solution. So looking at all these students' processes, and we had a lot of processes, we can come back to our systematic comparison of the frameworks of the problem-solving process. To remind you, this was what we found in the theoretical analysis: phases of understanding or analysis, phases of planning, exploration, devising a plan, looking back, maybe differentiated, and incubation illumination. We found phases or episodes of analyzing a problem, but there was no need to code a holistic episode like preparation where everything is tried out and then the students did not come to any further ideas. We found planning as well as exploration, so very structured and very unstructured ways of working on the problem. And we also found distinct episodes of just devising or working on a plan. We found episodes of looking back, but we did not find any signs for a further distinction into evaluation, so just looking at the solution, and internalization to try to learn from your problem-solving experience. And we also did not find any signs for incubation or illumination, especially not incubation, doing nothing for several minutes and just letting your subconsciousness work. This did not appear, which is not surprising because they were under constant supervision of a video camera. Looking at the linearity or non-linearity of processes, we have these three different types: strictly linear, cyclic at the beginning, and then linear or cyclic overall. To evaluate this, I looked at the episodes in the order that Polya or Schoenfeld proposed: analysis, exploration, planning, implementation, verification. And If a process proceeds in this way, even skipping an episode, it is considered linear. And if there is a step back, maybe from planning back to analysis or from verification back to planning, then the process is considered as nonlinear. Looking at this, we found 22 of 33 processes that proceeded in a linear way and 11 that were non-linear. Of these 11, 4 were of the type of Mason or Schoenfeld, with being cyclic only before an implementation and proceeding in a linear way afterwards. And the other 7 were cyclic in the way Wilson, Fernandez, and Hathaway described in their model, with being linear even after an implementation. Looking at metacognition or self-regulation, I'm going to skip this part because of time reasons, but I can say that in all the processes, there are signs of self-regulation and metacognition, and especially transitions between episodes are important signs of such activities. To sum up the research so far, it is possible to say that the phases of Poria seem to be more suitable to describe processes than those of Wallace or Poincaré with incubation and illumination. We can make a distinction between structured and unstructured procedures, especially planning and exploration, like Schoenfeld suggested. Planning and implementation cannot always be clearly separated, like Mason's attack phase. Sometimes they have to be combined, but sometimes they can be separated from each other. And processes can be linear or non-linear. So our model looks like this. Similar to Wilson's model, we arranged the phases in a cyclic way, and it is possible to go from one phase to the other. It is possible to have steps back, but you can also proceed in a linear way, and if you do so, every arrow points downwards. To discuss this so far, there are linear and non-linear processes. We found it to be important to be able to differentiate between planning and exploration, structured and unstructured. We also found that the activity of planning seems to be task or problem specific, also environment specific, more on this later. And we have to say that the setting might also influence the outcomes. So we, for example, we cannot expect illumination in such a setting. And planning or verification might also depend on the selection of problems. Okay, how to use this model. Here you can see the coding in the way Alan Schoenfeld suggested it, and we want to transfer it to the model I just presented. To do this, first we separate the different parts of the problems. For example, the 3 beaches A and B, the routine and the non-routine part of the problem. Then we ignore episodes or phases that are not task related, like reading or digression or writing down, when the students just do something that is not related to finding a solution or solving the problem. And then it looks like this. Here the process starts with an analysis. The students proceed to planning implementation. They go to verification, and then the process ends. There is one transition each. The second process looks like this. The students also start with an analysis. They go to an exploration. Then they go from an exploration back to analysis. There is a second transition from analysis to exploration, and then the process ends. The other example from the DGS environment looks like this. The students start with planning implementation. Then they go to verification. They go back to planning. From planning, there is a transition to exploration. After exploration, it goes back to planning implementation. Then there is a second transition to verification, and then the process ends. We transferred every process into this model. At first, you might think, why do this transformation? You just lose information. You do not see when these two transitions appeared or how long these episodes were. But after this transformation, we are able to accumulate several processes to do group comparisons. This can look like this. Here we have 7 processes of groups of students working on a routine problem, 3A, where the circumcircle of a triangle was asked. You see here the different outcomes transferred into our model, and then this can be combined. You see that of these 7 processes, 6 started with planning implementation, 1 started with analysis, 4 of these processes ended after planning implementation, and 3 went on to verify their results before ending the process. Doing this, we can look at the 2 routine tasks that are in our database. This is the one I showed you an example of. And here we can see that of these 15 routine processes, 12 started with planning implementation, 3 started with analysis, and 5 used the verification, whereas 10 ended after planning implementation. To compare this with the problem-solving processes, here just of the tasks 3 and 4. And here of all 5 non-routine problems that we used, you can see clearly that there are differences. In the routine processes, there are no exploration episodes at all. There are only a few analysis episodes and some verifications, but these verifications are all very short, which you cannot see in this model. In the problem-solving processes, there are a lot of analysis and exploration episodes. There are steps forward and backwards. As you can see, the routine processes are all linear, no arrows pointing upwards. We can also use the model and this accumulation of processes to compare the different environments, paper and pencil and dynamic geometry software. Looking at these and counting the transitions and episodes, we find even though the length of these processes are almost identical, there are some significant differences. In the DGS environment, there is more planning and implementation. 50% of the processes use planning implementation. In the paper and pencil environment, only 13% of the processes. In the DGS environment, almost 40% of the processes use a verification, and in paper and pencil, only 13%. There are more transitions, 4 per process in DGS and only 3.5 per process in paper and pencil. And if we think that especially transitions are related to metacognitive activities, then this might be an important difference. And what is not shown in the figure, there are more organization episodes. Organization was coded when the students tried to draw a table without further working on the problem, if it took them some minutes to do so, or tried to work with the software. And not surprisingly, in the DGS environment, there is a lot more time spent in organizing the technology than in paper and pencil environments. To summarize this, problem solving is not schematic and not linear. First do this, then do this, then do this, even though there are a lot of normative models that say exactly that. You first have to read the task, then you have to analyze it, then you have to come up with a plan and so on. Actual problem solving that is observed does not proceed this way, but there are steps back. So being on the wrong track, not having an idea how to solve a problem right from the beginning is natural and also important to become a better problem solver. Also, I think that students must have the possibility to experience all the phases. So if some teachers explain the problems in detail, the students never need to analyze a problem for themselves. So it is important that students can explore and work on problems on their own. Comparing the different environments, we have seen that especially at the beginning, the first problems, the students need additional time to work with technology, thus the organizing episodes, the time spent thinking about the software. The technology can be used in a heuristic way. The students can look at countless examples. They cannot have measuring errors and so on. But on the other hand, is there still a need for proofs? Or are they satisfied with the countless examples and measures they did? This will be explored in the future. Also, there seems to be a need for structures when working with technology. The students did more planning, had more transitions, did more verifications than in the paper and pencil environment. But maybe this is the case because they had more time, because looking for examples, measuring did not cost them as much time as in the other environment. There are more differences that will be explored in the future. So, thank you for your attention.